Okay.
Go ahead when you're ready.
Well, welcome everybody. For those that may not know who I am, I'm Chris Ellison. I'm a faculty member in chemical engineering and material science and senior investigator in the CSP. As is tradition, I want to start with a safety moment, which is related to the topic of today. That's working in a processing lab. A processing lab has a number of potential hazards that are maybe different from other types of laboratories, including rotating and reciprocating machinery parts, hot surfaces, high pressures, and in some instances, heavy equipment. So wearing proper PPE and being aware of the dress code is important. Of course, safety glasses are required in all laboratories, but you might take additional precautions, including heat-resistant or anti-cut gloves. Of course, no loose-fitting clothing, and your hair should be tied back. And the latter two are primarily to prevent from getting them caught in rotating or reciprocating parts. And as with all laboratories, never work alone. On the right-hand side, you'll see an image saying know your machine, and probably the biggest part of operating machinery safely is to be very aware of how it operates. And so these are all of the types of things you might think about as you work in a processing lab to promote safety. Okay, so I'll start our Beyond the Classroom, which we've titled Polymer Processing. I want to thank a lot of people from the Ellison group that have helped put this together. You'll see their names and their pictures as we go through, and you'll hear from some of them as well. I want to give special thanks to Boran Zhao and John Beamer, who helped make the Beyond logo with the two kneading blocks you'll see replacing the O. These are kneading blocks that you'd see as part of a screw in a twin screw extruder that's co-rotating. So it's relevant to the topic today. Also want to thank Chris McCosco, who helped give feedback on some early versions of this talk. So just to start, I want to lay a little bit of the foundation of polymer processing, introducing it, but also talking a little bit about how it's intertwined with material properties. Of course, processing polymers really increases their utility substantially. Processing can take place in the solid or liquid state, and liquid can be produced by way of heating to make a melt or by adding a solvent. But as you'll see in a moment, this often introduces non-equilibrium phenomena. Sometimes we take advantage of it to produce unique properties, and other times we'd like to reduce it to prevent other phenomena. Polymers can be processed in a number of different forms. The next image below shows thermoplastics, where you may heat a series of pellets, run it through a process to make a product, but you can also process thermosets by way of reactive processes. For example, if you wanted to make epoxy composites, you might take reactive monomers and process them in a carbon fiber woven mat. Processing typically doubles the value of the polymer if done correctly. And so below, I'm just sort of showing the flow of from cradle to grave, so to speak, or crude oil and gas entering at the beginning. Of course, in the Center for Sustainable Polymers, we hope that would be biomass or sustainable materials, and then finishing at product. And you can see it goes from $1 a pound to $2 a pound by way of the process. The process can be pretty complicated. Here I'm just showing a flow sheet of an hypothetical process for film. And really the only takeaway I'd like you to have here is that the process is more complicated than sort of the single units that we'll show you today. And you really need to think about it in terms of all the unit operations. Here I'm showing a film process just as an example. Okay, next slide. Polymers are anisotropic, and so this is typically exploited through processing. Because they're long chain molecules and have covalent bonds, they can be aligned in the flow. And that alignment in the flow can impart unique properties that can compete with more conventional materials. In the table below, I'm showing you the modulus, the strain at break, and the density for steel, glass, HDPE, and gel spun HDPE, which is a fiber spinning process. And you can see that HDPE that's just maybe ordinarily processed by, let's say, molding, the properties are not that competitive with steel and glass in terms of modulus, straight at break, et cetera. However, if you process it by gel spun fiber process, you can actually make fibers that are competitive with steel, but have almost 8 times lower density. And so this is a result of alignment of polymer chains. This is sold as several different commercial products, one by DSM called Dyneema, and the other by Honeywell called Spectra. So the role of the material in the process is actually quite important in defining the final properties. One of the ways you might think about how materials are intertwined with the process is to think about relevant timescales. Of course, materials have intrinsic material timescales. These might be related to things like the relaxation time, could be related to the crystallization kinetics. And these are dictated by things like molecular weight distribution, branches, physical aging, et cetera. But you have to think about those material timescales and how they work with the process, which come from the mechanical history, the flow intensity timescale, which can be different depending on the process that you're using, and then also the thermal history. Thermal history in particular is important by way of how quench rates may control internal stress in the system, or the crystallization kinetics, and ultimately the crystal content. So these 3 timescales are really important. Just to show a few examples of this, I'd like to focus on the rate of flow and how it can affect the way in which a material behaves. And here I'm showing low density polyethylene, the plot of viscosity versus shear rate. And you can see that the viscosity that the material exhibits in the process can be very different depending on the shear rate or the characteristic shear rate of that process. So you can see injection molding, extrusion, calendering, pressing, or molding, can all take on different characteristic shear rates. And this means that a given material may adopt several different viscosities in several different types of processes. I'd just like to point out that measuring the rheology or the viscosity of these systems over such a wide shear rate range typically requires you using several different types of rheometers: rotational rheometry at low shear rates, and then capillary rheometry at high shear rates. So rate of flow matters substantially. The type of flow is also quite important. And so here I'm showing the shear viscosity and the extensional viscosity, comparing low density polyethylene to linear low density polyethylene. And you can see that the shear viscosity of those 2 systems look relatively similar. They both shear thin, and they're not that different. However, if you look at the extensional viscosity, which is a different type of flow, the LLDPE doesn't exhibit much extensional strain hardening, while LDPE strain hardens substantially. And so the reason for this is LDPE is highly branched. It looks similar to LLDP in shear, but it's very different in extension. And this all comes from 2 polymers that are essentially all carbon and hydrogen. So keep in mind that processing operations can differ in both deformation rate and the type of deformation. And here's an example where both the type of deformation and deformation rate differs in a single process. So it's not as if you take one process and it has one type of shear and one type of shear rate. It can actually exhibit multiple types. So this shows the streamlines of the fluid, a polymer melt, let's say, and the size of the arrows indicate the velocity of the flow. And essentially you have a large tube going to a small tube. And where this contraction happens, there's a significant amount of extensional flow or mixed shear and extensional flow. Whereas at the ends of both ends of this picture, you typically just have simple shear and roughly parabolic velocity profiles. And so, this is a very simple flow, but it has very complicated type of shear rate and type of deformation. Okay, so this is the outline for our talk, and I won't spend too much time on this because you're going to hear from all these presenters. That's how we've divided it up. One of the comments I'd like to make from here forth is that we put this talk together with quite a few details in the spirit that you may access it at later time as a starting point as you begin to think about processing. So we may not cover every single detail. This isn't how I would normally put together a technical talk, but in the spirit of you having the information to access at a later time, we decided to put it together in this manner. So I'll now turn it over to Charlie, who will cover mixing and molding.
Hello, I'm Charles McCutcheon. I'll be discussing mixing and molding. I'd like to just note that if you have any questions about this section, feel free to reach out to myself or Kailong, and we'd be happy to answer them for you. And one more thing I would like to address at the beginning is that for all the mixers we will discuss, they can be used to mix polymer additive, and polymer filler type of blends. So the first mixer we'll talk about today is the Hake ReoMix Lab Mixer, which is a batch mixer. So the general process is there's a feed, so you could put in whatever type of polymer or filler you would like, and then it goes into a heated chamber where it is mixed. You could see two cross-sectional views, a lateral and a frontal view, and you could see a visual of the screws. The screws are counter-rotating, and you could see the mixing flows. Like I mentioned earlier, this is a batch process, and therefore one disadvantage of it is the material after mixing is a little difficult to recover. So this specific Hake mixer we have at the UMN is a Hake ReoMix OS Lab Mixer 900. So the batch size is about 45 grams, or you can do a smaller batch size about 20 grams with a spacer. You can do in situ measurements while mixing, such as the shear rate, which is proportional to the rotor speed, and the melt viscosity, which can be measured from the torque and rotor speed. So example of research that used the Hake at the U of M was done by the McCosco and Morse group, and they used it to prepare polymer blends, co-continuous blends in specific. They added a block copolymer which stabilized the blend, and you could see the results here. Another example of the Hake mixer is you can use a proper attachment when we don't currently have buckhead purchase, and you can measure other properties in situ during the melt mixing. Here we measured the electrical conductivity, which is monitored by the addition of carbon black to make a composite, is one example there. So next we'll talk about the twin screw extruder, and this is a continuous mixer while the Hake was a batch mixer. So we have a mixer here, and again you have a feed, so for polymer, fillers, additives, and then you have an extruder, a heating block, a die, and then once the filament comes out of the die, it can then be pelletized if you would like. So now we'll take a more zoomed in look at what goes on in the mixing section. So in the twin screw, you have two screws. You have a conveying zone and a melting zone, and then you have a mixing zone. The mixing zone is where you see those kneading blocks, which you saw earlier in the beyond the classroom figure. And in these kneading blocks, you have, this is where the mixing mostly occurs. So you'll have both shear and extensional flow, and it is very complex. You also then have a degassing zone, and then the material is discharged and extruded into parts. So the specific twin screw extruder we have at the U of M is a Prism 16 millimeter. It has co-rotating screws, and the screw speeds can go up to about 200 RPM. The throughput is about 0.05 to 10 kilograms per hour. And a disadvantage of a continuous mixer of this sort is that you need a minimum of about 50 grams of polymer needed. Though this is an industrially relevant process and has a high and can produce blends very effectively at a large scale. There's a lot of parameters involved with the twin screw extrusion. Some setting parameters are screw speed, screw design, and barrel heating. Some process parameters are the pressure profile, the temperature profile, and residence time. And I'd just like to reiterate that the process is complex and involves both shear and extensional flows. So in industry, a lot of times, twin screw extruder is used to make master batches in different compounds. One master batch example from the UMN is from the Ellison and Bates group, in which PLA is mixed with a block copolymer, at a production rate of about 500 grams per hour. And then this material is then used for film blowing experiments. And you can see from the tensile property curve that the Blockopolymer toughens the blends and gives the material better properties. Another example is PLA that has been fiber reinforced composite with the cellulose nanofiber. And as you can see, as you increase the cellulose nanofiber loading, the modulus increases. So I've showed you both a batch process and a continuous process. And now I'll show you a process that can do both, the microcompounder. This is a lab scale version of the twin screw extruder, the previous mixer you just saw. And as it can reach similar shear rates and does similar mixing, but is used for small sample sizes and usually R&D use. So if you look over here on this right figure, we have the polymer feed, conical twin screws for mixing, a recirculation chamber, which is to ensure proper mixing. And after your resonance is complete, you can then discharge the polymer into out the extruder, and then you can either produce films or a filament, depending on the die attachment you have. Typically, we produce filaments, but I will show you a die attachment in the future. So at the UMN, we have two different microcompounders, one with a 5 milliliter capacity and the other with a 15 milliliter capacity. And the ones we have at the UMM are counter-rotating screws, and they both have the ability to have a nitrogen atmosphere for an inert atmosphere. Some key processing parameters that you can tune is temperature and screw speed. The screw speed can be converted to the shear rate through this equation here, and the melt viscosity can be measured through the force and torque as seen there. So again, in situ measurements can be recorded while mixing. So this is the film die, which you can attach to the microcompounder, and you can then extrude films instead of filament. And the film will come out this little blue section here of the die, and then the rollers can be used to collect the films. So examples of microcompounding from the U of M are, so the first one here is from the Lodge and McCosker group, in which a batch process was used. So there they used reactive compatibilization of polyethylene and PLA blends, in which they added a catalyst, and the catalyst added, because the catalyst was added, a reaction happened at the interface of the two polymers and formed blockopolymers to reduce the interfacial tension, and therefore you could see the dispersion size decreased. A more recent example, one from the CSP, is a continuous process of polyurethane foams. So the microcompounder proved to be an effective way to remove, as well as an effective way to enhance the carbanion reaction in situ. And it turned cross-linked polyurethane foam waste, and then we're able to reprocess them into films. So this is now the molding part before we talked about the mixing. So the previous processing equipment was associated with mixing and injection, and this is going to be the injection molder, which will take those mixed polymers and make final products with them. So in this, for this machine, polymer is fed into the hopper, and then there's a heated barrel with which the material is pushed through with a piston, and it will be filled into a mold. So this process is used for high throughput of the same part, and you get very tight tolerances. So one material that's made this way are Legos. One disadvantage is that you need to machine and mold. You need to machine a mold, which could take time and is also expensive to make. So key parameters for the injection molder are the temperature and pressure. So if you don't have the right temperature and pressure, you're going to either overfill your mold or underfill your mold, and you won't have the proper product. At the U of M, two particular molds we have are a tensile bar and an impact test specimen. So one example of using the impact test specimen was in the Bates group. They injection molded to produce IZOD impact test bars which was IPP toughened with Blockopolymer, and then they were able to test all these impact bars at a very efficient manner. And another thing injection molding is used for is to study the effect of the chain alignment of fillers and just the chains and see how it impacts the material properties.
All right, great, thank you. My name is William Leonard. I go by Bill. I'm a recent postdoc with the Ellison Group. I started with them just before everything started shutting down. So it's great to be here with you all to be able to talk about some film processing. So often when you create a material, you want to characterize it in the solid state. It's very frequent you want to make it out of a film. And one of the easiest ways to do that is to dissolve it in some compatible solvent and then spin coat it, where you use a high-speed rotating substrate, and then the solvent evaporates, leaving behind your polymer film. And what's helpful about this is that it's pretty easy to tune the height of your film from some of these independent variables based on your solution's viscosity and how fast you're rotating. And one of the unique capabilities we have here is to do high temperature spin coating, which allows for us to make polyolefin films or liquid crystal polymer thin films as well. Next slide. So really, the things you need to think about when you're making these types of films is what polymer fraction you're going to use, and that increases the viscosity of your solution, and that gives you a kind of a base limit on what thicknesses you're able to access within the RPMs of the system. And some of the limitations here beyond that is you do lose material, so if it's very expensive, it might not be the most ideal. You might just want a regular just casting then. And then really it's not able to spin to coat irregular substrates. And in addition, we do have a companion bake plate, so you can remove any residual solvent to finish drying your sample for further characterization. Next slide. Next slide, please. So one way to mold a polymer film to an irregular substrate is with compression molding. And this allows you to access either kind of thicker films from the melt exclusively. There is no need for a solution or a solvent. And then it does allow you to get some basic irregular shapes as well. And the main parameters you have here controlling your sample properties are your heat and pressure, and then your hold time and some of your cooling characteristics. Next slide. And then what you further what you can do with this is if you have some pre-made films, either made from spin coating or from pressing them as films previously with the compression molder, you can laminate films and look at adhesive properties, diffusion between the layers, or some other interactions at the interface that you might find interesting. And again, the same kind of controlling parameters as your temperature, pressure, pressing time, and you want to consider the TG or TM of the materials that you're working with to kind of derive what process parameters you want to use. And so a specific example of what's been done here is the use of a block copolymer to act as a tie layer for between two incompatible polymers, where we see a substantial increase in adhesion between the two phases with this inclusion of the block copolymer that kind of entangles with both phases and ties them together. And then additionally, looking at reactive compatibilization. So the diffusion of the two phases causes the reactive groups on each polymer to interact, and then you get adhesion as well without the need to include a third phase, such as the block copolymers previously. So it's a kind of an in situ method to compatibilize two incompatible materials. And another kind of way to make thin films, specifically a bilayer system, is the use of our capillary rheometer with two barrels that allows you to co-extrude two films together, two polymer melts together, where the kind of limitations here is that each bore must be at the same temperature and piston speed. So you do have some limitations there, that will alter kind of your melt contact time a little bit. And then we're able to access a fairly wide range of interface contact times to examine kind of in situ reactions, or if you're interested in localization at the interface, this might be a good small scale method for you as well. So some things that's been done here is kind of in situ compatibilization, where we've examined kind of the effects of the polymerization type of the polyolefin and how they interdiffuse with each other, showing, and then also reactive compatibilization, showing we get better improved adhesion with this increased contact time, allowing you to kind of better understand scaled up process parameters. And another kind of step up from that, if you're looking for a higher number of layers or a higher number of interfaces, is multi-layer co-extrusion. This is a much larger scale. Each extruder you need about 500 grams for, and then it does have a fair amount of flexibility beyond that, where you can control your number of layers either from the onset at the feed block with the addition of layer multipliers, and then you can control your film size and thickness with your takeoff, your exit die, and any other post-processing that you might be interested in. Next. And so some of the special design considerations here is the combination of the high shear and layer confinement that allows you to kind of get this forced assembly. So for example, in a block copolymer system, alignment of a cylinder phase with the extrusion direction, and in a blended phase of polypropylene and polyethylene oxide, you can actually get the polypropylene to form a continuous fiber forming phase. And then further processing can be done on these systems to control the morphology with the confinement effects beyond that, giving you a 2D confinement instead of the 1D confinement you typically see from spin coating. And additionally, you can add a variety of additives to the system, where going back to that previous work, you could add block copolymers as an alternative route for recycling. You could include dyes. Dyes have been included for 3D optical data storage. Really, the only restrictions you have on the process are you want kind of your system to be in this viscosity range between 10 and 100 kilopascal seconds at this shear rate. And that gives you good layer integrity if your viscosity then is within 2 times of each other. So you're getting consistent layer thickness and throughout your whole system. But then again, you do have high sample requirement here. And kind of this last more unique system we have is this small scale film blowing system. This works on a similar capacity as the multi-layer co-extrusion, about 500 grams per extruder. And we're able to actually have 3 extruders here, so we can layer 3 polymers together, either one as a tie layer to looking at compatibilizing or adhering to incompatible polymer systems together. You can look at effects of blow up on your system, and we have pretty good control over the relationship between the flow rate and the operating speeds of the equipment. Thank you.
Hi, good afternoon, everyone. My name is Aditya. I'm a graduate student in the Ellison Group. And in this section, I would be talking about how the processing techniques are used to make fibers. So if I move to the next slide, just as a broad background, the typical types of fiber mats that are produced from polymeric feedstocks are broadly categorized into woven fibers and non-woven fibers. As the images suggest, woven fibers are those in which the individual fibers are stitched in a given pattern, while in non-wovens, the fibers are laid down randomly on top of each other, which are held together by physical interactions, or in some cases, they are also chemically bonded for a mechanical stability as well. So some of the applications which are very commonly used for fibers include disposable hygiene and medical products. For example, in this current COVID outbreak, you would have seen so much demand of N95 masks. So the main material of the N95 mask is basically a non-woven mesh of polypropylene. In addition to those disposable hygiene products, there's a vast demand of these polymer fibers in filtrations, as you can imagine as well, in clothings and textiles, as these pictures suggest. So some of the techniques in which these polymer fibers are generally made include conventional methods like melt spinning or solution spinning, in which typical fiber diameters are above 10 microns or so, while the advanced methods involve melt blowing and electrospinning, in which fiber diameters much less than 10 microns, even in the range of nanometers, are attainable. So the major if you go back one more time, so the major difference between the conventional and the advanced process is the way the fibers are drawn out, and also the viscoelastic property of the polymers that are used in this particular processes. For example, in conventional methods, the fiber is drawn by mechanical take-up wheel and winding that happens afterwards, which leads to the much higher diameter that is obtained. In comparison, in the advanced methods, there is additional drawing force. For example, high velocity air jets in melt blowing and electric field in electrospinning, which leads to much higher stretching of the fiber filaments, leading to much smaller diameter. In addition to that, from a viscoelastic point of view as well, the advanced methods typically involve much lower viscosity and elastic properties, leading to those particular diameter ranges. So the two processes that I would be focusing on is melt blowing and electrospinning. So as you can see, melt blowing has been commonly used in the industry for about half a century right now. So how it operates is basically the polymer is feed through the green hopper at the top, and once when it passes through the die, it is melt at high temperature above its glass transition temperature or its melting temperature, which is extruded through the die tip, and the hot air jets marked by the red arrows stretch them out into thin filaments, leading to further thinning and reduction in diameters, which during flight cools down below its solidification temperature and is subsequently collected down below in the rotating drum. The inset on the right basically highlights the mechanism by which this particular process is happening. Some of the common feedstocks, like I mentioned, in case of N95 mask, is like polypropylene and polybutylene terephthalates, which provides a high melting temperature, which basically gives the upper ceiling temperature up to which that particular polymer fibers are stable. The typical melt blowing temperatures are in the range of about 200 to 350 Celsius, while the viscosity ranges about 20 to 200 Pascal seconds for optimum performance as well. And as you can see from the fifth bullet point, the product, it's a high throughput method as well, which leads to a large scale production of polymer fibers in the industry as well. So moving on to the next slide, this is the particular equipment that we have at UMN in Amundsen Hall, in which a capillary rheometer is attached to a melt blowing die, which is shown in the blue inset. The capillary rheometer serves the purpose of pushing the polymer melt through the melt blowing die, which then, as I mentioned, gets drawn down into fibers, small, thin fibers, which are collected as in the bottom section as well. So a couple of research areas that has been studied in UMN includes the first one, in which polypropylene was used to produce nanofibers by fine-tuning certain processing parameters like the viscoelastic properties, the polymer delivery rates and all. So the highlight of this particular work was that since you can attain nanofibers, this opens up a large application area in which high specific surface areas are key for success. In addition to that, a recent paper also highlighted the fact that by using a polymer functionalized with a thermoreversible Diels-Alder network can provide a method in which you can get recyclable cross-link fibers, which also leads to a sustainable aspect of this particular technique. In comparison, in electrospinning, in contrast to polymer melt, in electrospinning, polymer solutions are used, which are drawn into thin fiber jets using strong electric field in the range of about 10 to 50 kilovolt or so. And due to the high stretching force that is available for this, the typical fiber diameters are in the range of 1 microns or even lower in the nanometer scale as well. Some of the typical polymer considerations that should be taken into consideration in this particular method include the molecular weight of the polymers that are used, the viscosity as well, and more importantly, the dielectric constant of the solvent being used, since electric field is such an important part of this particular process. So moving on, the current research in our group has focused on modifying these melt blowing and electrospinning methods through what we call UV cure blowing and UV electrospinning. So what sets these apart from the conventional processes is that instead of a polymer melt or a polymer solution, we use a monomer mixture, a reactive monomer mixture, for example, comprising of thiol acrylate monomers or thiol allyl ether or other thiol-ene monomers that are extruded through a die, which are then drawn by air jets or electric field in both the cases. And while in flight, upon shining UV light on them, there's a rapid cross-linking that occurs, which leads to formation of a cross-link network within the fiber mat, which is collected. So this also gives an additional benefit that you can get a cross-linked fiber mat at the end of this particular process. So in the next slide, I would just show a couple of videos which shows the UV cure blowing setup that we have in UMN in action, in which you can see that through the syringe on the left, the reactive monomers are extruded to the die, and during flight, upon shining UV light, they cross-link, which is collected downstream. While the video on the right basically is a high-speed photography of the fiber attenuation process that is happening, in which high-speed air is impinging on it from the top and bottom slits, lead to progressive thinning of the fiber jets as well. Thank you.
Can everybody hear me well?
Yes, we can hear you. You can go ahead.
Hello, my name is Boran Zhao. I'm currently a postdoc from Professor Allison's group. And in this last section of today's presentation, I will shed some light on additive manufacturing or 3D printing. Before I go on that, I would like to thank my colleagues listed here for their help in putting together this section. So the essence of additive manufacturing or 3D printing is to translate virtual 3D models from a computer into physical objects. So as compared to traditional way of material processing, 3D printing doesn't require extensive machining or molding. So oftentimes, 3D printing will greatly reduce the lead time in industry. And as new 3D printing techniques, new material coming out each year, and with improved hardware and software, we will see this trend of transform from rapid prototyping to rapid manufacturing. So among the 3D printing materials, polymeric material definitely plays a central role. And depending on what type of polymer you are interested in, there are ways of 3D printing method that can process that. Today, I will focus mainly on three most widely used 3D printing techniques. The first one is extrusion-based FDM. The second and the third are photopolymerization-based. They are SLA and UV-DIW. In the next slides, I will explain what they are, how they work, and I'll give an example for each of them. So the first technique I'm going to talk about is called fuse deposition modeling. So the picture on the top shows the typical lab scale, the size of lab scale FDM printer. And the video shown on the bottom shows a typical process of the printing. The principles behind FDM printing is pretty straightforward. So we fit in our filament, and the filament gets melted, extruded, and deposited on the building platform. Here, we listed some of the key parameters and dimensions timescale related to FDM printing. And one thing I want to point out that although there are a lot of thermoplastics commercially available filaments that we can choose from, for example, the PLA, ABS, or nylon, you can also make your own filament. And in the next slides, I'm going to give an example of making customized filament at UMN. The goal here is to 3D print a scaffold as a cardioidic patch using FDM. And shown in the video here, we use the twin screw extruder to make the filament. This is the same, exactly the same extruder that my colleague Charlie have talked about before. This is, as you can see, like we can, this material is a binary polymer blend, and we target the filament diameter to be around 1.7 millimeter, which complies with the requirements from the 3D printer. And here, as the picture shown on the right, this is the final product. And one thing we want to further develop is to study the drag release from this scaffold. The second technique I want to talk about is stereolithography, or SLA. As the video and the picture shows here, the SLA definitely basically converts the liquid resin into a cross-linked part by photopolymerization. It consists basically three major parts. The first one is a light source, could be either a digital light projector or a single point laser. The second part is the vat, which holds the liquid polymer resins. And third one is the moving build plate. Again, we listed some of the print dimensions here and time scale related to SLA printing. And the novel liquid resin for SLA process is definitely a focal point for research. And here is an example of the work done at UMN. This is done by Professor Rennike's group. In this work, normal acrylate monomers are developed from phenolic alcohols, and these alcohols are harvested from softwood lignin. They are sustainable, and results shown here demonstrate that they can not only generate successful SLA prints, but also the thermal and mechanical properties of these prints are comparable with the commercial SLA resins, for example, from Formlab. And moving on to the last technique I'm going to talk about is the UV-assisted direct ink writing. The printing principles looks a lot like a combination of a FDM printer and SLA printer. Here is a picture of the printer in Professor Francis' lab. It is converted actually from an FDM printer, and we added a UV light attachment. So the liquid resin was extruded from to the build plate, and it got solidified either continuously or sequentially. So the resin needs to have a certain yield stress to prevent the resin running away after deposition. And actually the material are quite flexible. We can use colloidal suspensions. We can use photocurable resins that can be converted from the SLA resin. And there are plenty of ways of converting a conventional SLA resin to a DIW resin. For example, adding a rheological modifier. And also I want to point out in the lab scale, we don't need quite a lot of materials. Usually we can generate a print using less than 5 milliliter, and the printing dimensions could be as large as 10 centimeter and could be finished within an hour. Here I'm giving you an example of the work done at UMN. So from Professor Allison and Professor Francis' group, we develop a dual curable resin from acrylates and polyurethane. So the green body is solidified by UV curing the acrylate component, and the polyurethane component is cured in a thermal heating process afterwards. As shown here, we can generate fairly high aspect ratio of these elastomers, and based on different components of acrylate and polyurethane, this print could be as in a rigid body or could be as extensible as elastomer, and these are perfectly suitable for soft robotic applications. And that's the end of my section, and I will turn it over to Professor Allison.
Okay. Maybe before I wrap up here, I just want to make a quick comment. Maybe some of you have seen Chris McCosco and myself chatting back and forth, but I don't let the scale of some of the instruments scare you. Some of them indicate 500 grams is sort of the scale you operate at, but there are really clever ways to inject a plug of, let's say, active material that may have some special chemistry incorporated into it, or some other special properties that you can inject a 50-gram plug in the continuous process to make a run of a sample that could be of interest to your research. So don't think that you need 500 grams exclusively. There are ways to get away with smaller amounts. So to conclude a little bit, I just want to point out that there's a lot of really nice references that you might take a look at as you start to think about processing. And these are just a few of them here. Obviously, there's many others, but I like these versions because they both broadly cover different processing operations, but also they really bring out the focus of the material and how it might interact or change its viscosity, et cetera, in different types of processes. So take a look at these if you have interest in reading further. And finally, I want to thank again all of the members of the Ellison Group that helped put this together. This was a non-trivial exercise to put all these slides together, and we got a lot of nice feedback from Chris McCosco, and I thank him again for his help. And this is the group not too long ago. Many of the people have contributed that you see here, and some of them have been presenters today. We'd love to collaborate with any of you. If you have other questions, please feel free to reach out to me or anyone that you've seen in the slides, and we can help get you started in processing if that's something you'd like to do. So I think I'll stop here and be happy to answer any questions that anybody has, as I'm sure the other presenters would too.